question? All right, thank you very much. I appreciate that. Then the next, we are going to have two short presentations. The first one is by Linda Al-Atick. She's right here. She's postdoc with Pierre. We are collecting and analyzing lots of data on a small magnitude. And this is the first very preliminary analysis we are collecting, and we are going to do much more. But Linda is going to show you the first preliminary results for about 15 minutes. And then Brian Chiou is going to talk about, again, behavior of a small magnitude data. Linda.
Good afternoon. As Yusuf mentioned, I'm going to be presenting some observations from a preliminary analysis on the magnitude dependence of the standard deviation of ground motion models for small to moderate magnitude data. As Norm mentioned, in the 2008 next generation attenuation models, some of the models had magnitude dependence sigma, like Abrahamson and Silva, Chiou and Youngs and Idris, while Bohr and Atkinson and Campbell and Bozornia had constant sigma models. It was thought that this magnitude dependence in some of the NGA models was the result of including aftershocks in the data set. So the objective of this preliminary analysis was to evaluate the magnitude dependence of sigma for small to moderate magnitude data, and to see if magnitude dependence can be observed using main shock data only. We also performed a preliminary sensitivity analysis to evaluate the impact of regional differences on the magnitude dependence of sigma. For this analysis, we used a data set from the Chiou et al. 2010 model that is going to be published later on this year. This data set consists of main shock California data with magnitude between 3 and 5.5 at 4 periods, peak ground acceleration, peak ground velocity, and periods of 0.3 and 1 second. Using this data set, we analyzed the standard deviations for two models, the Chiou et al. 2010 ground motion prediction model for small to moderate magnitude earthquakes, and the Campbell and Bozornia 2008 NGA West model. Brian is going to talk in more detail about the Chiou et al. Model, but I'm going to give you a brief overview. It's basically a small magnitude extension of the Chiou and Young's 2008 NGA West model. Was developed, like I said, for small to moderate shallow crustal earthquakes, and it incorporates regional difference in median amplitude between Northern California and Southern California earthquakes. The intra-event and inter-event residuals from the Chiou et al. Model were separated into half-unit magnitude bins, and the corresponding standard deviations were calculated. These plots here show the intra-event standard deviation sigma, the inter-event standard deviation tau, and the total standard deviation with magnitude. The standard deviations computed for small magnitude data are shown in blue. The dashed lines show average standard deviations for magnitude between 3 and 5.5, and the rest of the lines show predicted standard deviations using 4 NGA West models, which are Abrahamson and Silva, Bohr and Atkinson, Campbell and Bozornia, and Chiou and Youngs. These predicted sigma values were for strike slip main shock events with magnitude greater than 5 on rock. We see here these plots are for peak ground acceleration, and they show that on average sigma for small to moderate magnitude data appears to be larger than what's predicted by the NGA West relationships for larger magnitude data. These plots show again sigma tau and sigma total with magnitude at peak ground velocity. We see here that sigma appears to be constant with magnitude, while tau and sigma total seem to increase as magnitude goes up from 3 to 5 and start decreasing again with magnitude larger than 5. Again, on average, we see here that the standard deviation for magnitude between 3 and 5.5 is on the upper end of what's predicted by the NGA West models. At a period of 0.3 seconds, sigma tau and sigma total appear to be, again, magnitude dependent. The magnitude dependence for the inter-event standard deviation tau seems to be stronger than that of sigma. And on average, the standard deviation for small to moderate magnitude data is generally larger than a predicted standard deviation with most NGA West models for magnitude larger than 5 earthquakes. At a period of 1 second, the same pattern is observed. Sigma tau, sigma total appear to be magnitude dependent. The residuals from the Chiou et al. Model were also separated for Northern California and Southern California data, and the corresponding standard deviations were evaluated for the different magnitude bins. These plots show the total standard deviation with magnitude at peak ground acceleration, peak ground velocity at 0.3 and 1 second for the Northern California and the Southern California data sets. We see here that the total standard deviation for Northern California is slightly larger than that for Southern California. The difference is almost insignificant at long period of 1 second. We also see the same trend of magnitude dependence of sigma for both data sets. Now, the residuals from the Campbell and Bozornia 2008 model using the small to moderate magnitude data set were also separated into half-unit magnitude bins, and standard deviations were calculated. These plots here show the intra-event standard deviation, inter-event standard deviation, and total standard deviation with magnitude at peak ground acceleration. The standard deviations computed are in blue. The average are shown as the dashed line for magnitude between 3 and 5.5. And the solid red line shows the predicted standard deviation using the Campbell and Bozornia NGA West model for magnitude larger than 5. We notice here that on average, standard deviation for small to moderate magnitude data appears to be significantly larger than what's predicted by Campbell and Bozornia NGA West model. Also, we note that sigma appears to be constant at PGA, while tau is more magnitude dependent. Here are the same plots for peak ground velocity. Again, sigma seems more or less constant, while tau and sigma total increase as magnitude goes up from 3 to 5 and start decreasing again for magnitude larger than 5. On average, these standard deviations are also higher than the predicted, corresponding predicted values using Campbell and Bozornia 08 model. At 0.3 and 1 second, we observe the same pattern. Sigma tau, sigma total are magnitude dependent. This dependence is stronger for tau than it is for sigma, and on average, these standard deviations for small to moderate magnitude data are larger than what's predicted by Campbell and Bozornia model for larger magnitude data. These plots show the total standard deviation with magnitude for Northern California and Southern California data sets with the Campbell and Bozornia model. We see here that the standard deviation for the Northern California data set is slightly larger than for Southern California data set. And again, we see same pattern of magnitude dependence for both data sets. In conclusion, this preliminary analysis showed that the standard deviation of ground motion models for small to moderate magnitude data appears to be magnitude dependent, with average being larger than what's predicted using the NGA West models. This magnitude dependence was observed using main shock data only. Therefore, we know that it's not only a result of including aftershocks. We also saw that the standard deviations for the Northern California data are slightly larger than for Southern California data. And finally, both the Chiou et al. Model and the Campbell and Bozornia 08 model using the same small to moderate magnitude data set showed same trends of magnitude dependence of sigma. Now, this was all preliminary, and this whole analysis will be repeated in greater detail once we have the complete data set of small to moderate magnitude data from California. We will perform this analysis for the full range, period range, which is from 0.01 to around 10 seconds. We will also evaluate the effects of including aftershocks on the magnitude dependence of sigma, and also evaluate the variability in the data set with respect to the NGA West small to moderate magnitude data set. Thank you.
Great. Thank you very much. Great. Thank you very much. Any question for Linda for a small magnitude? I have to make one comment is that because people ask, so why you guys are interested in magnitude 3 and so on. One key reason, because there are some recorded ground motion in Central Eastern U.S. in low magnitude. We want to compare really apple to apple. That's one reason. But there are other reasons, because we have several events at the same station recorded and for a small magnitude and so on. So there are different reasons that we are collecting and analyzing small magnitude data. Any question for Linda? No? Okay. So Brian Chiou, who has started this business of a small magnitude, and his paper is going to appear soon in earthquake spectra, right? Did more analysis of small magnitude data, and he's going to show it. Thank you very much, Brian.
Thank you. Okay. Well, my talk is not going to be that paper to be published in earthquake spectra, I think. Instead, I'm going to focus on two issues that may be relevant to Eastern United States, even though those observations are made in California. Okay. Now, the first issue I'm going to talk about is the magnitude-dependent sigma. And Linda has talked about this same issue earlier, but focus on the smaller magnitudes. In my talk, I'm going to focus more on the larger magnitude, the sigma, both the inter-event and intra-event sigma. Okay, the second issue I'm going to talk about is about regionalization. Earlier this morning, both Norm and Julian talked about using regionalization as a mean to reduce sigma. So I'm going to give an example that I have done in California that shows it is, if done properly, then we can see significant reduction in the inter-event sigma. But I want to also mention that what Norm talked about this morning is in the fine small scale. What I'm talking about today is in a much broader scale. So there is some difference there. Okay. The magnitude dependence of sigma has been incorporated in some of the attenuation model, and some of the researchers don't think that exists, as you probably see it already earlier in Norm's and Gabe's presentation. So the empirical evidence of having a magnitude-dependent sigma is probably best illustrated in the study by Yang et al. In 1995. In that study, they have used about 800 or so PGA data that's all recorded in California. Okay, it's a decent data set. Okay, it's probably the largest data set that one can assemble at that time. And the analysis is done in the framework of mixed effect model, and so as a result, they can look at the magnitude dependence in both tau and sigma. Their conclusion is that the magnitude dependence of the variance, both tau and sigma, is statistically significant. Okay. Now, in the NGA program, that is for the Western U.S. NGA program, the same issue about magnitude dependence has been looked at, and different developer group come up with different conclusions. Some of the developer group feel that they didn't see evidence of magnitude dependence. As a result, they model the sigma as a constant. And some developer group see a magnitude dependence in their analysis, even though the dependence is much weaker than what has been observed in Yang et al. In 1995. Okay. One thing I want to mention here is maybe important is that all the NGA model includes some non-California earthquakes. That is the case. That is especially the case for large magnitude, that's magnitude greater than 6.5. So as you can see that on the right in the figure, there is at large magnitudes the inter-event sigma between the difference between the NGA model and the Yang et al. 95 model is quite significant. Okay, so that this discrepancy compelled me to revisit the Yang et al. Analysis to see if there's anything different between the two studies. that can explain the almost a twofold 100% difference in the estimated sigma. So, so to repeat the analysis, I put together a data set that's much larger than what Yang et al. Used in 1995. And that data set is the same as the one that was used in the Chiou et al. 2009 or 2010. It will be published in 2010. So in that data set, there is about more than 10,000 PGA data from both recorded in both Central and Southern California between the period of 97 to 2008. And to supplement that small magnitude data set, I have included all the California data that's available from the NGA database. And with the criteria that those earthquakes have to have at least 5 recordings. Okay. The criteria is there so I have some confidence in trusting the estimated inter-event term. Okay, so in total, I have about 2012 main shocks only. There's no aftershocks. Okay, and as part of the project, I've developed a small magnitude attenuation model for California that's based on the Chiou and Yang NGA model, but with modification to the magnitude scaling at small magnitude range. Okay, and the inter-event terms for those 212 main shocks computed relative to that small magnitude model is plotted in the top figures. Okay, as you can see that the scatter of those inter-event terms is the largest at small magnitudes. As you go to larger and larger magnitude, the scatter becomes smaller and smaller. Okay. Now, in the bottom plot, I plotted the intra-event residuals also against the function of magnitudes. And we see more or less the same, where there's a much larger scatter at small magnitude and smaller scatter at larger magnitudes. Okay. And one thing I want to mention that in this new data set, there isn't much new California earthquake larger than magnitude 6 since the 95 study by Yang et al. The 3 new magnitude, the 3 earthquake that happened since 95 is the Hector, Mayans, and Simeon and Parkfields. So, so at large magnitude, we basically have about the same data set as the Yang et al. Study. Just to illustrate how the sigma and tau dependent on magnitude, what I did is I grouped the data into half-unit magnitude bins, and then I calculate the tau and sigma for each magnitude bins. Okay? And I plotted in these figures. Now, I plotted the mean estimate. I didn't have the error bars in there, but just want you to know that there are some uncertainties with the bin estimates. Okay? And that uncertainty will become larger as we go to larger magnitude because the number of data points becomes smaller. Okay. Overall, we see a strong magnitude dependence of those beam estimates as a function of magnitude. And the other thing that is interesting to note is that the NGA values, which is represented by Abramson-Silver's model, plotted as red, is much higher than the bin estimates at large magnitudes. Okay. So, as I mentioned that in the NGA models, there are a lot of foreign data that's in the large magnitude range. So what I did is I put those foreign data into my database, and I redo the analysis, and to see how, by including the foreign earthquake, how that would affect the estimate of the sigma or the tau. Okay. So, and that estimate is shown as the pluses. As you can see, once I include the foreign data, the bin estimate becomes consistent with the Abramson-Silver's estimates. Okay. So I did the same thing for sigma, and that's plotted in this figure. And again, we see a magnitude dependence in sigma. Okay. In this case, all three studies are more or less have pretty good, reasonable agreement among the three models. So, so what is the implication of what I just showed you to the NGA East studies? Okay. In the NGA East, a hybrid empirical method that was proposed by Ken has been used to develop attenuation model for the eastern United States. And in his methodology, the host region is California. Okay. Now, by saying, now remember, we see there is a large discrepancy in the large magnitude tau between California-specific model and the NGA model, which represent the global, which is a global model. Okay. So that discrepancy, I think it's large enough to warrant a investigation or further investigation into a California-specific ground motion model, in particular for the taus. Okay. Now, the second issue I'm going to talk about is the regionalization as a way to reduce inter-event sigma in California. Okay. The reason why the inter-event sigma can be reduced because by regionalization, we actually remove the region-to-region or systematic region-to-region variability in the median. Okay. And this approach is most effective for small magnitude, where the regional variation is likely to be larger. Okay. Okay. Now, this is this figure shows the inter-event residual as a function of magnitude for three different analyses. Okay. The analysis on the left is a calculation relative to attenuation model that does not have any regionalization, meaning treating the state of California as one single region. Okay. And by doing that, I come up with a inter-event sigma of 0.55. Okay. Now, so one thing to know that is that I also group the data into the Northern California or Central California, which is shown as the triangle, the blue triangles, and also the Southern California, which is shown in red. As you can see from the plot on the left, the inter-event term for the Central California earthquake is systematically lower than those from Southern California. Okay. Now, and that difference is the largest at small magnitude. As you go to higher magnitude, when you approach 4 and 5, the regional difference becomes smaller. Okay. Now, based on this plot, we go ahead and do another model. But in that model, we have used the network boundaries between the Northern and Southern California network as the dividing line. Okay. And we allowed the attenuation model to have different magnitude scaling for Northern and Southern California. And the inter-event residual calculated from that model is shown in the middle. As you can see that compared to the one on the left, those blue triangles now move up. The red square now move down a little bit. The two sets have become much more consistent. Okay. Now, at the same time, we also notice that there's earthquake in some part of the Southern California seems to systematically showing lower than average event term. And those earthquakes are shown as solid red squares. Okay. And to help you see where those earthquakes are located, I mapped the event terms in these figures. What can I get? Oh, here. So you can see that in Southern California, which is in this box, the event turn on the western transfer ranges are systematically low, meaning it has negative residual, inter-event residuals. As you move to the east, when you get into the eastern transfer ranges, the inter-event residual becomes positive. Okay. Now, and we noticed that this pattern is very similar to a stress strap pattern that was obtained by Scherer and others in 2006 for micro-earthquakes, less than magnitude 3. Okay. So and I have reproduced his figures here. Now you can see that the negative residuals, inter-event residuals here, correspond to lower stress drop over here. As you move to the eastern transfer ranges, you see a high inter-event residual that corresponds to large stress drop in Scherer's map. Okay. So this is quite amazing because these two studies are done using different set of data, using different methodologies, but they come out with very similar patterns. Okay. So observing that, we decide that we maybe the network boundary, which is about here, is probably not the best we can do. So we say we're assuming, we're just hypothesizing that maybe the 118-degree longitude is a better dividing line for the regionalization purpose. So we did that. We do another regression analysis using the 118 degrees as a dividing line. So you can see that if we do that, the data or the inter-event scatter becomes much tighter, okay? And we get a much smaller tau. Okay? So you can see from here is that without regionalization, we got 0.55. If we take the network boundary as the dividing line, we get 15% reduction in tau. And if we choose another one, 118 degree as the dividing line, we get 30% reduction. Okay. So this comes to my last slide, which is about regionalization. It's a good idea, and it could be very, the reduction that we can get from the regionalization could be significant. However, the amount of reduction depends on the boundary you use. Okay? And the best boundary may not be the geological boundary or even not a network boundary. So the challenge in using regionalization as a way to reduce inter-event sigma is really in the selection or identifying the appropriate regional boundaries. Okay. Thank you. That's my.
Great. Thank you very much, Brian. Question for Brian. Any question for Brian? Frank. Oh, sorry. 1 second.
How about using the boundary which you see in the stress drop distribution? So if you would cluster the stress drops from Peter Scherer's work, and then you get some polygons and use that as regions,
Yeah.
would you expect another amount of reduction in sigma?
Well, I think in the slide I show there is that the point is that there is a similarity in the pattern between our inter-event residual map and the stress drop map that's developed by Scherer et al. Okay. So if this similarity is also true for other region, okay, then we can use the smaller magnitude, the stress drop from smaller magnitude, as a way to help us define the boundaries. Okay. So is that?
No.
An issue we're going to face is, so in your context, this is kind of like those eta sub SR numbers that we were talking about here, right? In those little pieces of the source region term, that this area has a higher stress drop on average, this area has a lower stress drop. But we're going to have to just do the, let's say, 3s to 4s, the stress drops from those, are those good predictors of the 5s and above? And so that we're going to be left with that recurring theme.
Right.
How much do small magnitude stress drops tell us about big magnitude stress drops?
Well, that's one of the main conclusions from our paper is that the difference we see in small magnitude does not directly translate into difference in large magnitudes. So there is the the regional difference is not just an offset. It's a magnitude there's a magnitude dependence in the regional difference.
Arvin?
I'm wondering, someone who has not done any ground motion processing, whether there is present any measurement error. That is, if you give the same record, original raw record to different people, and they baseline correct or process or whatever, if there is variation coming from that, I'm just stipulating.
Yeah.
It is possible that you will observe maybe larger sigmas for small magnitude, therefore small recordings, because typically maybe the error there is larger. I'm wondering if anybody has investigated or thought about the possibility of the influence of measurement error.
Bob?
Well, I call it measurement error because what you're using is measurement, a record, and the question is whether there's error. People use those records, PGA, PGV.
This is the
PGD.
fellow who is processing literally 10,000s of records for here. Bob? Yeah.
Bob?
Here.
There was a large study in the first NGA group where we reprocessed basically all the data we gathered from USGS and CSNP at Pacific Engineering and Analysis. And then we compared the response spectra from our filtering to the original filtering. And within what most people call the usable data bandwidth, which is between the 3 dB points at your low pass and your high pass, on average, there's zero bias. Now, when you go outside the corner frequencies or extend the data, then there can be large differences between different processors. And this has been found for many years in processing. And now with the newer data that we're starting to look at for the NJ East project, since the data is recorded on higher quality instruments, the processing differences are much, much smaller. Most of the differences occurred on SMA instruments, which are analog and digitized, and there's still quite a bit of judgment on where you looked, where the noise occurred. CSNP judges the noise looking at response spectra. We and some other groups judge the noise looking at Fourier amplitude spectra. Some groups filter all three records the same. We filtered all three records differently. So, but in the bandwidth that we shared in common between our filter corners, there was no difference averaged over the entire data set.
Very good. So now the next